All right, hello everyone. We're looking at 4.5 day 1, and we're going to talk about how to graph sine and cosine functions. And here we have the parent function, so these are going to go over the basic shapes and the vocabulary that we're going to use at the bottom of page 1. These are the specific formulas, if you will, the methods we're going to use to find each of those values. And then on the next page, we're going to learn how to assemble all of those values to graph it by hand. All right, so one thing you'll notice is that we're going to do this in radians and not in degrees. But the basic shapes of our sine and cosine functions come from the unit circle. So I'm going to draw just a really tiny unit circle just for reference here. All right, so here we're just using the quadrant angle. So 0 pi, pi over 2, pi, 3/2 pi, and then back at the beginning, 2 pi. All right, so that's a total of 1, 2, 3, 4, 5. That means we'll use 5 critical values on the shape. And if you think about the point on the graph of our unit circle, remember the radius is 1. So that means this point would be located at 1, 0 at the top, 0, 1, and just working our way around to fill that in. Notice we're ignoring all of the angles that are between those quadrant angles, and even though they exist on the unit circle, that's just too much information for us to try to plot every single point on our sine curve. So we're using these as major landmarks so that we can hit the maximum and minimum values, and then we'll draw the curve between those. All right, so I've said in the past that our sine function is paired up with the y-coordinate on the unit circle. So when you're looking at this equation of sine x, remember this is just a symbol for the input. It might be easier to think of it as sine theta. The input is always the angle of rotation from the unit circle. So we're not saying you plug in the x coordinate. No, that is just a symbol to say this is where the input goes. And then this is your output. What are we calculating? Well, the output is going to be the y coordinate of the unit circle. So if we think about what that means for us, then on our scale, we want to work in radians, and we'll start here at 0 pi radians. And just to space it out, just to give us a little bit of room here, I'll skip every other grid line. So pi over 2 radians, and then pi radians, and then 3/2 pi, and then 2 pi. And again, just to give us a little bit of space here, I'm going to skip every other grid line, and that's going to be my radius of 1. From the unit circle. So what we're saying is that if I have a rotation of 0 pi radians, then my y-coordinate is at 0. So I'm going to plot a point here. At pi over 2 radians, that's my input. The output is the y-coordinate on the unit circle, which is 1. So we're plotting a point here. At pi radians, the y-coordinate is 0. At 3/2 pi radians, the y-coordinate is a -1. I'm sorry, I put that in the wrong spot, didn't I? Let me fix that, put it here. And then at 2 pi radians, that y-coordinate is 0 again. So you can see that we have this curve that starts here on the axis, goes up to the maximum, back to the midline, down to the minimum, and back to the midline. So I call this the midline, but it is the axis of our graph. So either way works. So here are some vocabulary words. What we have then is our axis, which happens to be on the horizontal axis as well. But if we have a vertical shift up or down, it'll take that axis and push it off of the horizontal axis of the grid. So this is the axis, sometimes referred to the midline. And then we have a distance from that axis to that maximum point. That's going to be the amplitude. So the amplitude is the distance, and it's a positive distance. So even if we measure that amplitude down to the minimum point, it's still referred to as the amplitude. But even though I have a negative value on my graph, amplitude is always positive, because it's a distance. It's a distance from the axis. Okay. from the starting value to the ending value, that represents the length of one cycle, which we refer to as one period. And that period is subdivided into 4 equal parts. So each of those 4 equal parts has the location of the critical value, which is that quadrant angle. So from 0 to pi over 2, that's 1/4 of the total length of that cycle. From pi over 2 to pi is another 1/4. This is 1/4. This is 1/4. So there's 4 equal-sized parts, and this is referred to in several different ways. Sometimes more casually, I call it the jump, because I'm just saying, hey, you jump from 0 radians to pi over 2 radians, and we skip all the radian angles in between. So in a more casual sense, we're jumping from one quadrant angle to the next. We also call this the interval. We also call this the scale. So it's referred to by a variety of different words, but there are 4 equal-sized parts of that. So the jump is the scale on our axis. Now, if you take a look at this sine curve, it just so happens that the sine curve doesn't really stop at 2 pi, but it keeps on going. If we were to go around the unit circle a second time, then that sine curve would continue. And if we go a third time around the unit circle, then it would continue even further. And if we go backwards around the unit circle, then that means we would have a sine curve continuing to the left. So, even though we're drawing clear starting and stopping values, that just represents where we are showing one complete pattern, one complete cycle, before it repeats itself. The cosine function has some similar aspects to it. Again, our horizontal scale is going to be at 0, pi, and then pi over 2, and then 1 pi, and then 3/2 pi, and then 2 pi. And again, on that vertical scale, I'll use the same set as my previous graph. So again, with the cosine, our input is the angle of rotation, and the output is describing the x-coordinate of that point on the unit circle. So this is the x-coordinate of the unit circle, and that's what we're plotting here on this graph. So at 0 rotations, we have an x-coordinate of +1. So our first point starts here. That's our first critical value. We jump to pi over 2, and our x-coordinate is 0. We jump to pi, and our x-coordinate is -1. We jump to 3/2 pi, our coordinate is back to 0, and then finally at 2 pi, we're back to 1. You see this V-shaped pattern here, but when you draw it, don't draw straight lines. It's not an absolute value graph. You want to give it a little bit of an almost horizontal or very shallow curve at the maximum and minimum points, and then curve kind of steeply, almost at a 45-degree angle there, through those second and fourth critical values. And so once again, you have your midline, your axis, right? You still have your amplitude that takes you up to that top part there, the maximum point. You have your amplitude, which takes you down to the minimum again. So all of those same words show up here as well to describe the vertical spacing between the maximum and the minimum. And then again, you have your horizontal spacing, which again is that period, which is divided into 4 equal parts. Okay, now what we're talking about in some of these other characteristics here, just to finish it up, the period is not just 2 pi, the period is all real. I'm sorry, I need to start over because I'm confusing my period with my domain. The domain is all real numbers because the graph goes on forever. But yeah, the period is the length of exactly one pattern, so I need to edit myself there. That is the 2 pi, and that's true for both sine and cosine. The range is describing the height of the graph, and so we are going from -1 up to +1. And that finishes up our little characteristics of the parent functions of sines and cosines. So that means when we are graphing sines and cosines, we'll have this basic set of 5 critical values, but we're going to manipulate them with the transformations, and this is how we calculate those. So we might have a sine or a cosine as the pattern, but we will have possibly the A in front, which is the vertical stretch. Inside the grouping symbols is the B, which is the horizontal stretch or shrink. We have the C, which is the horizontal shift, right or left, and then the D is your vertical shift, up or down. So that's what those 4 letters are representing. We used to use H and K for the horizontal and the vertical when we were graphing by hands with other functions, but here we use C and D instead of H and K. So what does the A actually do? Well, yeah, it's a vertical stretch, but it affects the amplitude, because if you have a vertical stretch that makes it taller, well, then that means the amplitude is a bigger distance. Notice it's always positive with the absolute value. B affects the horizontal stretch, which is the length of the period. So normally the period is 2 pi radians, but we might stretch it out or we might compress it in. So we calculate that by taking the 2 pi and dividing by b. That would be the period, the cycle length. Then we're going to take that result and find the jump, or the interval between those critical values, which will be the scale on our horizontal axis. So we take the period and divide it into 4 equal parts. The letter C is affecting the starting and the stopping point if we have a horizontal shift, but it's really both B and C that might affect these, so that's why you see both B and C showing up here. So it'll be easier to see in the examples we're going to do here, but the idea is you take everything that's in the parentheses and you set it equal to 0 because that's where your sine curve normally starts. Or you set it equal to 2 pi because that's where your cosine or your sine curve normally stops. Now that axis, or that midline, is going to be a horizontal line at that number, whatever the value of d is. So if it's a vertical shift of up 2, then at y equals 2 is that horizontal line. So we'll come back and use this as a way to sort of organize the information as we assemble the graph by hand. But I'm going to teach you a method that I refer to as the box. We're going to draw a box around the space, and then we're going to put the curve inside the box. So if you imagine for a moment that the top side of our box is established by the amplitude, and the bottom side of our box is established by the amplitude, and the left side of the box is established by the starting point, and the right side of the box is established by the stopping point, what we're doing is creating sort of the boundaries in which will fit our 5 critical values. So when I say draw the box, what I really mean is let's figure out where the amplitude is, let's figure out the starting point, the ending point, and then we'll squeeze the shape of the curve into the box. So that's what I'm going to show you here. Let me turn the page over and we'll get started with example number 1. All right, so here in example number 1, we have this function. It is 3 times sine of x over 2. Well, that's not quite right in the standard form. Remember, we want our value of b to be in front of the x. We don't want it in a denominator. So we're going to reformat this slightly to look like 3 times the sine of 1/2 x. So instead of thinking of it as x divided by 2, think of it as 1/2 times x. That's the value of b. And then you can think of there being parentheses around that. So a is 3, b is 1/2, there's no c, and there's no d. So let's find the amplitude. So again, how we do this is all on page 1. The amplitude is the absolute value of a. So the absolute value of 3 is just 3. To find the period, we're going to take 2 pi and divide it by the value of b. So here's 2 pi divided by b, which is 1/2. So we have to simplify that. Remember, when dividing by a fraction, we are instead going to multiply by the reciprocal. So 2 pi times 2 gives me 4 pi. So that shows us a horizontal stretch. Now here in the notes on page 1, it's labeled as the jump. Here in the example, it's labeled as a scale, but they're meaning the same thing. We're going to take the period that we just calculated and take that value and divide it by 4. So we're subdividing that into 4 equal parts. So we take that 4 pi, divide it by 4, and you get pi. So that is going to be the scale on your tick mark. We're going to count using pi as the interval. And so I'll fill that out in just a moment, but that's what the number does for us. the starting point and the stopping point, we're going to take everything that's in the parentheses and set it equal to 0 because that's where the sine curve normally starts, and then we'll set everything equal to 2 pi because that's where the sine curve normally stops. So for me, that's the 1/2 x. We set that equal to 0, and then to calculate this, we're going to multiply both sides by 2 to isolate the variable, so we get x equals 0. So in other words, there's no horizontal shift, and we kind of already knew that because the value of c was 0. We aren't moving right or left. To find the stopping value, again, take everything in the parentheses, set that equal to 2 pi. Isolate the variable, we'll multiply both sides by 2. And so we get x equals 4 pi. So if you think about the distance between the starting and the stopping point, that should match the period that we calculated earlier. If you get a distance that is much bigger or smaller than the period length, then we know there's a mistake in our math, and that's just a bit of a self-check. Lastly, we're looking at the axis. And so again, that axis, or that midline, is a horizontal line at y equals some number, the value of d. In this case, our d is 0. So y equals 0 means there's no shift up or down. I know there's a minimum and a maximum here, but I'll fill those out later. We don't really need those in terms of graphing it, meaning what we have so far is enough to draw the box, the boundaries, and then we'll fit the curve in there. So the sequence of steps is generally this. We're going to start off with drawing the axis, then the amplitude. So that'll establish the top and the bottom of our box. Then we'll do the start and the ending points. That'll be the left side and the right side. But it would be really helpful if we had a scale on our graph. So let's continue finishing up labeling our scale. So the horizontal scale is going up by units of pi. So 1 pi, 2 pi, 3 pi, and 4 pi. We can go further if we need to, but we know already we're stopping at 4 pi, so we really don't need to go further. If we had to go in the negative direction, well, then we can count -1 pi, -2 pi, and so on. Now, we're starting at 0, so we actually don't need any negatives, but just so you know, we might have a horizontal shift that pushes us left, and we can still count in the negative direction, even in terms of pi. On the vertical scale, I'll just go by ones. All right, now we're ready to graph. So step 1, we're going to draw that axis. That axis is the horizontal reference that we use. This is placed at 0, so it happens to be also on the horizontal axis of our grid. From there, we then find the amplitude. The amplitude is 3, so that's going to be a distance above and below the axis. So 3 units above puts us here at +3. This will be where my maximum points are placed. And the amplitude of 3 units below the axis puts us here at -3. So this is where the minimum points on our curve will be placed. So that's the top boundary and that's the bottom boundary. So that's really what the minimum and maximum are describing here in the notes. Our maximum is there at +3 and the minimum is at -3. Now for the starting values, the start is at 0, so this is the left boundary of my box, and stopping at 4 pi, this is the right boundary of my box. So what you have here is the space where we're going to put in our curve. All right. Now we analyze the 5 critical values. We're just checking to see, is it a sine curve or a cosine curve? You can see it is a sine curve. And so that information is on page 1, but the pattern for the sine of those 5 critical values is this. First point is at the midline, second point is at the maximum, third point is at the midline, then we go down to the minimum and then back to the midline. So that's the pattern of the 5 points that we want. So for us, what that means is my first point is at the starting value at 0, which is the left side of my box. So that's on the axis. Then we jump to the next tick mark at 1 pi, and now we're at the maximum point. Then we jump to the next tick mark at 2 pi, so now we're at the midline again. We jump to the next tick mark at 3 pi, so now we're at the minimum point, the bottom side of the box. Then we jump to the next tick mark at 4 pi, and we're back to the midline. So those are the 5 critical points equally spaced out, and then we freehand the curve like so. Now remember, that's just one cycle, and we'll be graphing one cycle. But remember that the sine curve goes on forever, and so if we were to use this as our pattern, and if we had to graph two of these, well, we could just copy and paste it down like that. And there we would have two full cycles. All right, that's the general process. So these other examples are just to take you through the sequence of steps so that you can see, again, just by repetition, how we calculate all of these values and then how we assemble them into the box and fit our curve in there. So let's go on to example 2. So here we are in example 2. We're dealing with a cosine graph this time. So the value of A is 3. The value of B is right in front of that input, so that's a 2. The value of C is, well, it's not negative pi. I don't know if you remember, but we always change the sign when we take out that horizontal shift. In other words, we're not shifting left, we're shifting to the right, a distance of pi units. Okay, that's what it's communicating. The value of D is negative 2, so that would tell us we're shifting down 2. So that's just a little description of what that number is telling us. So that means our box is going to shift to the right and down, so we would expect our graph to be somewhere down here. Okay, the amplitude is the absolute value of A, which again is positive 3. The period is 2 pi divided by the value of B. Well, B is exactly 2, so we're dividing by 2, and that means we have a cycle length of 1 pi. We take that result and subdivide it into 4 equal parts. So that will be the scale. So on my tick marks, I'll be counting in terms of 1/4 pi, and I'll fill that in a little later on. For the start and the stop values, we take everything in the parentheses, 2x minus pi, and we set this equal to 0 because our cosine graph normally starts at 0. For the stop, we take everything in parentheses, the 2x minus pi, and we set this equal to 2 pi because our cosine graph normally stops at 2 pi. But because we're manipulating the placement of it, we might not be starting and stopping at the same places. Let's see where we start and stop. So we'll solve for x in both of these. So I'm adding pi to both sides as I work to isolate the variable. So 2x equals pi, and then divide both sides by 2. So we get x equals pi over 2. That's going to be my starting value. Again, for the stopping value, let's first add pi to both sides. So we have 2x equals 3 pi, and then divide away the 2. So x is 3/2 pi. And then the axis is the value of D. That's a horizontal line at -2. So those are all the numbers. Let's put the scale on our axes, and then we'll assemble the box. So our horizontal scale is going up by pi over 4. So we're counting in terms of fourths of a pi. So this first tick mark is 1/4 pi. The next one is 2/4 pi. But if you think about that fraction, 2/4 reduces to 1/2. So we're not writing it down as 2/4 pi, we're writing it down as 1/2 of a pi, or pi over 2. So we had 1/4 pi, 2/4 pi, here's 3/4 pi. Then we come to 4/4 pi, but again, that fraction also simplifies to exactly 1 pi. So that's my 4/4 pi. Here's my 5/4 pi. Next is 6/4 pi, but again, that fraction of 6 over 4 reduces to 3 over 2. So 6/4 pi becomes 3/2 pi. And then on my vertical scale, again, I think we can just go by ones. And now we're set to graph. So what we do is we always start with the axis. The axis here is a horizontal line at -2. And then from the axis, we're going to find the amplitude. We'll count 3 spaces above. 1, 2, 3. This is the top part of the box. And then from that axis, 3 spaces below. This is the bottom part of the box. So that gives us the max and min that you see here in the notes. So our maximum is at +1, and the minimum is at -5. The starting value is at pi over 2. So here's pi over 2. So this is the left side of the box. And the 3/2 pi is the right side of the box. So I just dash these lines in because they're not really there. They're not really part of the graph itself. It's just a framework for us to be able to use. If that's hard to see because I'm using a lighter color, then if I darken them in a little bit so you can see them better, there they are. But keep in mind, they're not really part of the graph. It's just a technique we're using to plot the 5 critical points. So what are those 5 critical points? Well, we're using the cosine pattern. So again, this is on page 1, but the cosine pattern is the V-shaped pattern. So the first critical point is at the maximum, then you jump down to the axis, then you jump down to the minimum, and then right back up again. So you can see that V-shaped pattern, but of course we're going to give it that little bit of a flare as we give it the curve. So that means at my starting point, the left side of the box, my first critical value is at the maximum. So I'm here at the top left corner. Then we jump to the next tick mark, and now I'm on the midline. So be careful you don't mark it here on the horizontal axis. We want it here on the midline. Then we jump to the next tick mark, and we're down here at the minimum point, so the bottom edge of the box. We jump to the next tick mark, and we're back to the midline. We jump to the next tick mark, and now we're returning to the top. So that's your V-shaped pattern, and again, curving it out like that. So again, that's just one cycle. Sometimes book problems will say, hey, draw 2 cycles. Well, you just take that and you just duplicate it, right? You just sort of copy and paste it right next to each other on whichever side you have room. Here we're just drawing 1 cycle because that's the basic building block. We could copy it indefinitely if we had to make it really big. Okay, so we've seen one of each. We've seen sine, we've seen cosine. I'm going to go through yet one more example. We'll finish up with this one today because there are a few details we need to keep in mind, and that's what we're going to talk about now. So one of the details that comes up here is the fact that this value of b is not just a whole number, it's in terms of pi. So how do we handle this when we have a value of b with pi? So we're going to talk about that. Another detail that comes up is just determining what this positive 1 is. Is that a value of c or d? Is that a horizontal movement or is that a vertical movement? Well, in our standard form, if we have a value c, it must be inside the parentheses. If there's no parentheses, then that means it's automatically outside of the parentheses. So that is a value of d. So c is nothing, d is positive 1. Think of it as if you had parentheses here, just with the b and the x. So our amplitude is the absolute value of 2. The period is 2 pi divided by b. Well, the b is that fraction of pi over 4. So let's see what happens when we divide by pi over 4. Again, we want to multiply by the reciprocal of that. So rewriting that as 2 pi times 4 over pi. You see that the pi's will cancel out because you have pi over pi. And that just leaves you with the numbers of 2 times 4 is 8. Now, what in the world is that number representing? Because up to this point, our period has always been in terms of pi. Well, remember, pi is about 3.14 radians. Okay? So what we have here in example 3 is just 8 radians. So that's a whole lot bigger than pi radians, isn't it? So we are having a horizontal stretch. To find the scale, we're going to take that period, subdivide it into 4 equal parts, and that means our scale is 2 radians. So remember that horizontal axis is always representing the input. The input is always an angle of rotation. Usually our angle of rotation is in terms of pi, like what we saw on example 2, but it doesn't have to be in terms of pi, but it's still radians. It's not 2 degrees, it's 2 radians. For the starting value, we'll take what's in parentheses, meaning the pi over 4 times x, set that equal to 0 because sine normally starts at 0. And then take that same pi over 4 times x and set it equal to 2 pi because that's where your sine curve normally stops, and we'll solve for x in both of these cases. I'm going to multiply both sides by 4 because I'm trying to eliminate that denominator. We have pi times x equals 0. Divide both sides by pi. Guess what? X is still 0. That means there's no horizontal shift, right? We're still starting at 0. Let's see where we stop. Multiplying both sides by 4. And then dividing both sides by pi. The pi's cancel out on both sides, and again you get 8. So these values should confirm what we calculated previously. If the period is a length of 8 radians, well then, if I'm starting at 0 and stopping at 8, that should be a length of 8 radians. And so yeah, that does match our previous calculation. The axis then is a horizontal line at +1. So those are all the values. Let's go and fill out the scale. So again, on the horizontal, we're counting by 2 radians. And then on the vertical scale, let's see, we're going to go up 1, amplitude of 2. I think, again, we can just go by ones here. So 1, 2, 3, and so on. Okay, so we're ready to graph. Step 1 of graphing is to start with that axis. So that's at +1. So there's my midline. And then we find the amplitude. The amplitude is 2. So 2 above puts it at 3. And 2 below the midline puts it at -1. So those are the maximum and minimum values. So maximum is y equals 3. Minimum is y equals -1. We're starting at 0 and stopping at 8. So there's the box. So then we find our sine pattern because we're trying to graph sine. And again, there it is. There's the sine pattern that we jotted down in example number 1. So we start at the midline and then go up to the maximum before coming back down again. So on my left-hand side of the box, I'm starting at the midline. Then I jump to the first tick mark and I'm at the maximum. I jump to the next tick mark, I'm at the midline. I jump to the next tick mark, I'm at the minimum. I jump to the last tick mark and I'm back to the midline. So there's those 5 critical points in that pattern. So then we freehand the curve. Now, while that's essentially it, I need to show you one more example. We're just going to build onto this one. So call this example 3A. And we're just changing one little detail, and let's see what happens. I'm taking the original equation, and the only thing I'm changing is, what if we happen to have a negative in front? Fortunately, we don't really have to redo everything. We're just communicating what happens to the graph if I had a negative in front. Well, you might remember when we graphed by hand in the past, a negative sign indicates a reflection, right? So in this example, just kind of filling in the space here, that is telling us that we have to reflect upside down. So what would that really change here? Well, the amplitude is still positive, because if we were to try and take the absolute value of -2, you still get +2, so the number stays the same. The period is the same, because that's based off of B. The scale is the same. The start is the same. The stop is the same. The axis is the same. The only thing that changes is that we have to reflect it upside down. Let me again grab a sheet of tracing paper to show you how that reflection works. So here's the sine curve. Here's the midline. Now what you have to be careful of is when you reflect it upside down, don't make the mistake of trying to reflect it over the horizontal axis of the graph that you're using. In other words, if I reflected it over the horizontal axis of the graph itself, it would end up down here, and now my curve is outside of the box. And we can't have that. That's an incorrect reflection. We're trying to do it upside down, but it landed in the wrong spot. What you have to do is reflect it over the midline itself, so that when you are placing that reflection, notice it still fits inside the box itself. So let me use a different color here so it stands out on my paper. So I'm going to reflect this in blue. So what used to be a maximum is now a minimum point. What used to be a minimum is now a maximum. So we're still inside the box. And so what you have here in blue, that's the -2. of the sine of pi fourths x plus 1. So that's just a little mini example added onto the original example to show you what happens if we have a reflection.